Hey guys, welcome to your 5.1 notes on rate of change and slope. Guess what? They mean the same thing. Haha. By the end of the day, you will be able to find rate of change from a table. You will also be able to find slope because they're the same thing. So when we talk about slope, let's talk about lines. So you see lines here. We've got a bunch of different lines. Lines can go both up and down. And they go up and down at different rates, or more generally, steepness. And let me show you what I mean by that. So here we've got this hiker, and he starts out with this casual climb. He's going up a little bit. Oh, by the way, I've sorted this into like sections of his route, of his hike. Okay, so he's going up, and he's going up pretty slowly. And then he goes down, and then he goes up real fast. Ooh, that's tough. And then he goes down. Oh, yay. And then he goes down faster. Oh, wow. And then he goes up again, kind of casually, generally, and then shoots right down. Okay, so we have a bunch of different sections going up. This goes up. This section goes up too. And we have some sections going down. This guy goes down. This section goes down. This section goes down more. And this section goes down even more. So today we're going to talk about that steepness. We're going to talk about slope. A lot of times you'll see slope called rate of change because that's exactly what it is. It shows how quickly something is changing. It shows the relationship between two different changing quantities. We'll see this in like X or Y a lot. Quantities. Okay. So when one quantity depends on the other, you'll remember that we have a dependent variable. Our dependent variable is I can't write and talk at the same time. Dependent. Our dependent variable is usually our y. We also have an independent variable. Our independent variable is usually our x. It won't always be, but usually, okay? So what we do is first we look at how they are changing. We look at the change in the dependent variable, and then we look at the change in the independent variable, and then we divide them by each other. So the rate at which something changes, rate of change, we're going to say that is equal to how fast the dependent variable is changing compared to how fast the independent variable is changing. So let's look at an example. You've got a marching band, and we want to figure out, are they marching at the same speed every time? Is their distance changing the same rate as their time? Is the rate of change constant? If so, what does the rate of change represent? The rate of change represents their speed. It's the distance they cover in a certain amount of time, and we call that speed. Just like you would have miles per hour, feet per minute as your speed. Or your velocity, if you want. Anyway, okay. So let's do it. Let's see how quickly this is changing. I'm going to go ahead and split this into two sections. First, we'll look at from the first minute to the second, then from the second to the third, and then from third to the fourth. Okay, so from 1 to 2 minutes, from 2 to 3 minutes, and then from 3 to 4 minutes. Let's go ahead and split your paper into 3 sections. Our first section is looking at the first minute to the second minute. So we want to figure out what is the change in distance, what is the change in y, compared to the change in x. And that's going to be our rate of change. Well, from 1 minute to the next, our distance changes from 520 or rather from 260 to 520. So to find out how big of a change that was, that's 520 minus 260. And then we changed by 2 seconds, minutes, sorry, from 2 minutes to 1 minute. So we do 520 minus 260, which is 260, divided by 2 minus 1, which is 1. So that's 260, feet per minute. By the way, I have no idea if that's like fast or not, so that's exciting. Okay, that's our answer. Let's highlight it in brown. 260 feet per minute. Okay, from our second to our third minute, we started out at 520, ended up at 780. So to figure out what that distance was, we figure out, okay, how quickly does our y change? How quickly does our x change? So our y changed. We have a gain of whatever 780 minus 520 is. And our x also changed. We have a gain of whatever 3 minus 2 is. That's 1. So that is 260 over 1, giving us, 260 feet per minute again. I like this, I like this, I like this. Oh, and spoiler alert, yes. You end up doing 1040 minus 780 all over 4 minus 3, which is 1, is 260 over 1 is, 260 feet per minute. Woo! So it is the same the whole time. They're marching at the same speed all day. Good job, guys. Good endurance. Okay. So a little bit of a reminder from last time when we talked about linear functions. Linear functions, we said, were lines. The graph takes the shape of a line. And in a linear function, the rate of change doesn't change. We say, actually, I'm not going to give it away. So we call that constant. The rate of change is constant. The rate of change is also called the slope. Ooh. That means it's increasing at the same rate the whole time. Now, I've claimed that the rate of change here is equal to the change in the dependent variable times, over the change in the independent variable. Let's clean this up. First of all, rate of change, we decided, no, we're going to call that slope. So that's very exciting. And what is our dependent variable here? It's a y. So it's just the change in y over the change in x. Oh shoot, I didn't mean to erase that whole thing. Okay, so we want to find out how quickly is y changing? How quickly is x changing? Now remember that y represents how far up and down you go. So our change in y is going to be our distance up. And then our change in x is going to be our distance to the right. And that will always be true. Okay, so let's look at it. Here in this graph right here, it doesn't go up, it goes down. Yikes. We want to figure out how do we get from this point to this point. Well, first let's look at our change up, which is actually down. How far down is that? 1, 2, 3, 4. We went down 4. And then across here, how long did it take us to go down 4? We went 1, 2, 3, 4, 5. Nice. Now because we went down, I'm going to call this a negative, like we went up -4, like that. Okay. Cool. Now, change in y is itself even cumbersome. Another way to say like how far we went up, we can just call that rise. And how far we went to the right, it's really verbose. Let's just say run. So here's your shortcut. Here's your shortcut. Slope is rise over run. That's all you need. Remember it, love it forever. Slope means rise over run. And in this case, our run was -4. Oh, sorry, not our run, our rise. Our rise was -4. Our run was 5. So our slope is -4/5. Ta-da! Again, slope is how high you go and how much time it takes you to get there. So we went down 4/5. This is also really nice to remember because we go over, and this number is over something. So it's down far over 5 because the 4 is over on top of the 5. So that's a fun trick. Now that brings me to our slope formula. We said earlier, slope is your change in y over change in x, and to find how something changes, that's a subtraction problem. So slope is always going to be the difference between, so it's like the difference between this y value and this y value. So it's whatever -3 minus 2 is. You need to figure out what that distance is. Oh, sorry, those are not our y values. Our rise is whatever 2 minus -2 is. So we need to find the difference between two y's. But we can't just do y minus y. We need to do, okay, it's second y minus the first y. So we say y2 minus y1. And then the same process applies. We need to find, okay, what is the difference? Remember, minus means difference. What is the difference between these two x's? So figure out, okay, well, what is 2 minus -3? So we take x2 minus x1. To show you how this works, I'm gonna plug them in. First, we need to assign, hey, this is point 1, this is point 2, so we keep our heads on straight. In this example, y2 is the y belonging to our second point, so that is -2. And in this example, it's y belonging to our first point is 2. And then we have x2 minus x1, so we need to take x belonging to our second point, which is this guy right here, 2 minus a -3, oh my. Okay, so we got 2 minus -3 and -2 minus 2. Let's see what that works out to be. Well, -2 minus 2 is -4, and 2 minus a negative is plus a positive. Oh, hey, look, it's the same. What a big surprise. I'm so surprised. Okay, cool. Man, I just did an example. Oh well, we're going to do another one. Extra practice. Remember to assign your numbers to your points. So say, hey, this is point number 1. This is point number 2. Okay, cool. So I've got my x values. I've got my y values. Sometimes, literally, guys, it is so helpful to just go in and label your points and say, hey, you know what? I'm going to make this x and y because that's what they are. Because this is point 1, you've got your x1, y1. And here's my x2, y2. If you have to literally write that right above those to help you keep track of what your numbers mean, that's great. I do that. So anyway, y2 is -2. y1 is 0. x2 is 3. x1 is -1. And now we need to find those subtractions. -2 minus 0 is -2. That was nice. -3 minus -1 is 3 plus 1 is 4. Oof! But we can simplify that. That's the same thing as -1/2. Guys, slope will not always be negative. It just happened to be in both of these cases. Speaking of not being negative, it can also get super funky. Okay? So here, the slope of the line, I'm going to run through it. I'm going to put the slope here for you guys. I'm going to prove to you something weird. Okay, so let's make this point number 1. Let's make this point number 2. And we plug our values into our slope formula. Hopefully you've noticed something weird about this line. It is a straight, flat line. That is weird. Now let's show you what happens when it gets weird. Okay, so we've got our x values and our y values. Oh, hey, our y values are the same. Y is the same. That's weird. We should take a note of that somehow. So when y is the same, we'll get 2, actually, to save you to get sometime, we get 2 minus 2, which comes out to 0. So it doesn't really matter what happens down on the bottom. You have, 2 minus negative 3 is 5. Well, 0 divided by 5, it's 0. Guys, when you have a horizontal line like this, the slope will always be 0. And you can remember that because Z has horizontal lines on it. So 0 slope. The slope equals 0. Ta-da. Okay, well, what happens when we do this? We've got a vertical line here. Got our points. We need our formula for slope. Y2 minus y1 equals x2 minus x1. I mean, not equals. Slope is y2 minus y1 all over x2 minus x1. By the way, we use m to represent slope. Fun fact, m for move, because it's describing how the graph moves, I guess. Sure. So if we plug in our y2 minus y1, etc., y2 minus y1 is negative 2 minus 1 all over negative 2 minus negative 2, giving us a plus 2. So, hey, look, our x's are the same. That's notable. We should take note about that in our Notability app. Aha, okay, anyway. So negative 2 minus 1 is negative 3 all over negative 2 plus 2 is 0. You can't divide by 0. That's against the laws of everything mathematical. Because you can't divide by 0, we don't have a definition for that. We call that undefined. There's no definition for it. So you can remember that because, u is a curve, so that's not going to help. But n in undefined has the vertical parts, so that will help you remember that it's undefined. So vertical line has undefined slope. Horizontal line has a slope of 0. And you can always use the slope formula to help you. Also, here's a cheat sheet for the different types of lines. Different types of slopes of lines. I'm going to go this way. Yeah. Go ahead and divide your paper into 4 sections and draw a cute little graph in each of them. It will be super chill. So if you have, like a X and Y axis like that, go ahead and put that into each section of your graph right here. Amazing. So good. Phenomenal. Now let's say you have a line that goes up like this. It just goes whoosh. Oh, that's not even the right tool. It goes whoosh, pop, like that. If it's pointing up, we say this line has positive slope. Cool? Cool. On the other hand, if you have a line that is pointing down, whoosh, like that, we say that line has negative slope. You remember this from our previous example where we had a line going down like this. That line had a negative slope. It was negative 4/5. So that's fun. We also saw 2 special kinds of lines. We saw a line that was vertical, but this line is horizontal, so don't let that throw you off. When you have a horizontal line, that has a slope of 0. And then we saw a line with a vertical slope. And whenever you have a line that is, when you have a vertical line, it's not the slope is vertical. When you have a vertical line, the slope is undefined. So there you go. And, if you're going to put your cheat sheet here, you might as well just also put the definition of the slope of a line as well. Say that slope is y2 minus y1 over x2 minus x1, which is the same thing as rise over run. So now you have everything you need to know right here. Slope is your change in y over your change in x. It's how far up you go and how far right you go. And there you go. Have a wonderful time in your homework.